This is the fifth video about the wind turbines, and in this video we are going to talk about, we're going to discuss the energy conversion efficiencies for different kinds of wind turbines, drag-based turbine, lift-based turbine. The efficiencies we are talking about is the first law efficiencies. It's basically just the total amount of output, useful output energy divided by the total amount of total amount of input energy. So before we start our discussion, let's there's a few quantities that we need to actually discuss. One quantity is basically the energy, right? So how much energy is actually in the wind that's actually blowing onto the wind turbine, right? The first quantity, this quantity, is E energy equals to, here we are only accounting for the kinetic energy inside of the wind, right? The mass times velocity squared divided by 2, right? For wind turbines, kinetic energy is probably sufficient for us to actually get started. The input power is basically the temporal rate of change of the energy, right? So most of the time we're actually concerned about the power, right? Power is the amount of energy or the amount of work created in a unit amount of time, right? So so the power is the temporal derivative of the energy, right? The power P is the temporal derivative of the energy, dE over dt. Right? So if we actually bring the expression of energy into this temporal derivative, then it's d mv squared divided by, over dt divided by 2. Right? So here we have to make an assumption. So in most of our analysis, for wind turbines, we are assuming for steady flow, or assuming that we're dealing with a steady airflow. A steady airflow actually means the flow velocity v is actually constant. So v doesn't change with time. So if the velocity doesn't change with time, then we can consider v as a constant, or v squared as a constant with respect to time, right? So a constant can be actually taken out of the derivative. So the power becomes dm over dt, right? And then multiply with v squared divided by 2, because v squared now is considered as a constant with respect to time, right? And then what exactly is dm dt, right? dm dt is actually the mass flow rate, right? How much mass is actually changing per unit time, right? So that's exactly mass flow rate, how fast the mass actually is flowing. So so the mass flow rate can be computed from what? From the density times the cross-sectional area times the velocity, right? So that's a unit, that's the amount of mass change throughout a unit amount of time, right? So if you actually multiply velocity with time for a certain duration, right, and that duration is a unit, right, that's called a 1, right? So v multiplied with time, which is time interval, that's 1, right? And then that's going to give you a distance, right? So distance times cross-sectional area, that gives you volume, right? Volume times density, that gives you the mass, right? That's the amount of mass that's being changed throughout a unit amount of time. So if you actually take that as dm over dt and then multiply v squared divided by 2, you get the total amount of power in the wind, which is rho a v cubed divided by 2. Right? So the amount of power, the amount of input power in the wind is actually proportional to v cubed. Right? So if you double the speed of the wind, then the power is actually 8 times. It's actually 8 times increasing in the power, right? So that's why we need to actually find places with high wind speed in order to actually set up a wind farm, a profitable wind farm, right? So speed of the wind is the most important factor that determines the power of the wind. The second quantity we must pay attention to is the force. The force. We know that the force is the temporal rate of change of the momentum. The momentum is basically just the mass multiplying the velocity. Right? So P equals to mass multiplied the velocity. That's here. It's a small case P. It's not the power big case P here. P here small case P actually represents momentum. In practice, in reality, velocity, the velocity is actually a vector, right? It's not a scalar. It's not just a number, right? Vector also has directions, so velocity also has directions, right? So momentum is also a vector. It has directions. But in our case, in our discussion following, we will just ignore the direction of the velocity and just treat it like a scalar. But in reality, you must know that momentum and velocity are actually vectors. They are not scalars. Right? And then force is just the rate at which momentum changes with time. There's a typo here. It's not moment. It's momentum. Momentum changes with time. Right? So F actually equals to the time derivative of the momentum, P. So it's dP over dt. So for a body with a constant mass, if the mass doesn't change with time, then F equals to dmv over dt, because the momentum is m times v, right? M times v over dt. If m is a constant, it doesn't change with time, then we can take it out of the time derivative, right? So it becomes dv over dt. V is the speed, so dv over dt, that's acceleration. So that gives us Newton's second law, F equals to ma. Right? But for studying the wind, for studying the airflow, we have to use the equation in a different way here, because mass is not really a constant with respect to time. For steady flow, for steady fluid flow, V is a constant with respect to time. So in this case, V doesn't change with time, but mass does change, right? So in this case, we have to actually take the velocity out of the time derivative, right? It becomes dm over dt. So it's dm over dt times v. So that's a quite significant difference from the usual form F equals to ma that we are familiar with, right? This is something that we are not familiar with. So dm over dt times v. dm over dt is what? dm over dt is again mass flow rate, right? The mass flow rate. So here I am writing out the mass flow rate explicitly. So mass is what? Mass is density times volume, right? Density, rho, times volume. Volume is cross-sectional area times the length. The length in the direction of the flow, basically, right? And then the whole thing take derivative with respect to time. If we assume the density and the cross-sectional area doesn't change with time, density is very constant, actually. So close to 1.25 or something. So density and cross-sectional area doesn't change with time, right? So takes the density and the cross-sectional area out of the derivatives, it becomes dl over dt. L is the distance in the direction of the flow, right? So dl over dt becomes v. That's the velocity, right? The time derivative of displacement is velocity, right? So it becomes rho av, and you still have another v outside of the bracket, so rho av squared. So force equals to rho av squared, right? Power equals to rho av cubed divided by 2, right? And in practice, it's not the momentum, the entire momentum change is being converted to a single force. It's not like that, right? You have to consider other factors. For example, the velocity has to be partitioned into, or momentum has to be partitioned into different components, that kind of thing, and other factors. So in practice, it's not really the entire momentum change is being converted to one type of force, right? So when we are considering just the drag force, for example, Fd, right? So it's the momentum change times some kind of a coefficient in front of it. Here we call it Cd. That's the coefficient for drag force. This is basically just a constant. And then if we are considering lift force, then we have a different coefficient. That's Cl. So usually you have to sort of multiply these kind of constant factors in order to actually get the force. In order to actually get the force you want to get to. So before we discuss the horizontal axis wind turbines, let's try to get a rough estimate of the vertical axis Salmoneus type turbine, which basically operates on the drag forces. There might be some small amount of lift forces, right, caused by the shape of the blades, that kind of thing. But in principle, it's a drag-based machine. Right. Here we are actually looking at a top-down view of the machine, of the turbine, right? And the wind actually blows horizontally from the left at a speed of u. And the blade has a total area of 2a, so it's split in half, right? So this half has an area of a, and this half has another area of a. So the entire area is actually 2a. But because half of the blade is actually shielded from the wind, so you have a shield, circular shield here, right? It's actually hiding this half of the blade from the wind. Because half of the blade is shielded from the wind by this half circle, so the area the wind can actually push on is actually a, this half. Right? And then the distance from the rotation axis to the edge of the blade is r. The rotation axis is here. That's the rotation axis. Right? So wind blows from here, right? Then it's going to rotate, and the axis of rotation is right here. Right? And from the rotation axis to the boundary to the edge of the blade, the distance is r. And the blade is rotating at an angular speed of capital omega. It has an angular speed of omega. So the linear speed at the edge of the blade, if you compute the linear speed, so angular speed is omega, right? And then the radius is r, right? So the linear speed at the edge of the blade is omega times r, right? So if you actually consider this particular linear speed of omega times r, and then you have a wind speed that's u, then the relative speed between the edge of the blade and the wind is what? Is u subtract omega r, right? Because the edge of the blade is actually moving in the same direction as the wind, right? It's moving at the same direction as the wind, omega r. So the relative speed between the wind and the edge of the blade is just the subtraction of these two speeds, right? That's the relative speeds. If it's actually rotating in the opposite direction as the wind, then it's u plus omega r, right? But it's rotating in the same direction as the wind, so it's u subtract omega r, right? That's the relative speed, right? And because the direction of the motion of the blade is actually in the same direction as the wind, right? We know that the drag force dominates in this kind of situation. Right? The lift force is almost negligible. It's almost negligible, right? In this kind of instance. From the previous slide, we know that the drag force is equal to the density, right? The density of the air multiply the area, right? The cross-sectional area, and then multiply velocity squared, and then a constant factor CD, right? So here we're gonna use exactly the same expression. So density times cross-sectional area, that's big A, right? And then times the square of the relative speed, right? The square of the relative speed, that's the effective speed, right? That's the square. And then multiply the coefficient, drag coefficient in front of it. But we have to know that this force is actually acting at the edge of the blade, right? And at the center of the blade, which is the rotation axis, the blade is actually stationary. It's not really moving at all. It has a speed of 0, right? So So if we actually consider the um, the average force acting on the entire blade, then we can just take the force on the edge and then divide by 2. Right? So here we divide by 2 to actually sort of account for this kind of a uneven distribution of the force from the edge to the center. So in principle, you should do an integral, right? You should do an integral that goes with r goes from like 0 to r, right? With the distance goes from 0 to r to actually get the total amount of force. But here we just do a really simple calculation just by using a 1/2. Right? And then what's going to be the power, right? The power is basically the force times the velocity. The force times the distance is actually the work. The work is the amount of energy, right? Energy, but power is the time derivative of energy, right? So time derivative of distance is actually speed. So it's force times speed. Force times speed actually gives you the power, right? So we have an expression for the force now, right? And then what's going to be the speed, right? Speed, let's just use omega r, right? Just use omega r. Again, it's a linear speed. Right? And then we can actually assemble all those expressions together. We can bring this expression into to replace the FD and then multiply with omega r, right? And then we do some algebra, take a rho A, right? Take a rho A, and then we take out a u cube. We take a u cube out of the multiplication, right? So rho A u cube, and then inside of the square bracket, it's going to be CD, and then the whole thing here divided by u cube, right? The whole thing here divided by u cube. And at this stage, we can introduce something that's called a speed ratio, lambda. The speed ratio is basically just the linear speed at the edge of the blade divided by the wind speed, u. That's the speed ratio, right? And then the power can actually be represented using lambda, this particular speed ratio, right? So after you have taken out the u cube, then the whole thing here has to be divided by u cube, right? And then you're going to get omega r divided by u, that kind of factors. And all those factors can be replaced with lambda, with the speed ratio. And then eventually you end up with this expression, right, in terms of lambda. The reason that I'm taking out the u cube is going to be quite obvious right away. Because the power in the wind, from the previous slide, we know that the power in the wind is what? The power in the wind is rho A v squared, the speed of the wind cubed divided by 2, right? That's the wind in the power here. The reason that we don't have a divided by 2 here is because the cross-sectional area, the entire cross-sectional area is actually 2A, right? Even though half of the blade is actually shielded from the wind, that just means that half of the wind energy is being wasted, right? But we still need to actually account for the total amount of power in the wind by using the entire cross-sectional area, that's 2A, right? So that's the entire power in the entire input power in the wind. And then if we want to get the conversion efficiency, eta is just the power extracted by the turbine divided by the input power, right? The input power is rho A u cube. Rho A u cube cancels out. What you are getting is this thing. So the efficiency is actually equal to this expression in terms of lambda. Right. So now we have to decide what might be a suitable lambda in order to actually maximize the efficiency eta. Right. So eta is a function. CD is a constant, but eta is a function of lambda. If we want to find the maximum of eta, then all we have to do is to take a derivative of eta with respect to lambda. Right. So d eta d lambda equals to this expression. Right. And then we set the derivative to 0 and solve for lambda. And this equation actually has two solutions. One is lambda equals to 1/3, and the other solution is lambda equals to 1. Right. But which one is actually gives us the maximum efficiency, right? So lambda equals to 1 is a quite interesting situation, right? Which means that the speed ratio actually equals to 1. Which means the speed of the blade is exactly the same as the speed of the wind. So the blade is just blown together with the wind. It has no relative speed. The relative speed is exactly zero. The blade has exactly the same speed as the wind, right? So the blade is moving together with the wind. The relative speed is going to be zero. In that case, the force is going to be zero, right? Because the force actually depends upon the square of the relative speed. If the relative speed is zero, then the force is zero, right? If the force is zero, force times velocity is zero. So the power extracted from the wind is zero. Right? So when lambda equals to 1, the efficiency is actually zero. You got no efficiency at all. So you have no output, power output. And there's another quite interesting situation is when lambda actually equals to 0. When lambda equals to 0, which means omega r is 0, right? It means what? It means the blade is exactly stationary. It's not moving at all, right? So basically this is not a rotating blade, it's just a solid wall. The wind cannot move it, right? If that's the case, the relative wind speed is going to be the maximum, right? So in this case, omega r equals to 0, right? U subtract 0 equals to u. The relative speed is maximum, right? It cannot exceed the speed of the wind because it cannot actually rotate against the wind, right? It can only rotate in the direction of the wind, or stay stationary without any kind of speed, right? So the maximum relative velocity is exactly the wind speed of u, right? So when lambda equals to 0, relative speed is 0, right? But again, relative speed is 0, omega r is 0, right? In this case, even though Fd, the drag force has been maximized, right? The drag force is maximized, but because omega r is 0, so the power output is still 0, right? Because nothing is moving, nothing is generating power at all, right? So when lambda equals to 0, it's eta is 0. When lambda equals to 1, eta is also 0. So we know that the optimal lambda must be between 0 and 1, right? And then we have 1/3. Indeed, 1/3 is the optimal value for lambda, right? And when lambda equals to 1/3, which means what? Which means the relative speed, the speed ratio is 1/3. So the speed of the blade is about 1/3 of the input wind speed, right? And in this case, eta max equal to CD times 2 divided by 27, which is about CD times 7.4 percentage point, 7.4%. Right. For a square blade, if the blade actually looks like square, CD is close to 1. It's 1.1 or something. Right. So if we multiply these two together, it's about 8% or something. Right. It's actually quite low efficiency. For modern horizontal axis wind turbine that operates on the lift force, we will use the classic actuator disk model. It's a very classic model. It's actually quite clever. We consider a stream tube. In this case, we're considering a stream tube, three-dimensional stream tube that looks like that. The axis of the stream tube is perpendicular to the swept area by the wind turbine blades. And the wind also blows in the same direction as the axis, so wind actually blows in this way, right? So if we take a side view, so this is a three-dimensional perspective view, right? But if we actually look from the side, if we actually look from this direction, we actually look at from this direction, the boundaries of the stream tube is indicated by these two dashed lines. Right? The boundaries, that's the boundaries of the stream tube. And the turbine swept surface is represented by this black line, the black vertical line, right? And the wind speed is horizontal in this kind of direction. And we're assuming this actuator disk, this disk that's representing the turbine swept area, is infinitely thin. Right? It has a thickness of 0. Right? So So we will be looking at both the pressure and the wind speed at 4 different positions. 1, 2, 3, 4. And on this perspective view, it's 1, 2, 3, and 4. That's the 4 different positions. We're going to look at the pressure and the speed at those 4 different positions. Position 1 is very far. It's actually very far from the turbine. It's at a far distance upwind. Right? If it's in front of the turbine, we call it upwind. So position 1 is at a far distance upwind. Right? And then position 4 is at a far distance downwind. Right? It's at a very far distance downwind, so it's not affected by the wind turbine anymore. Right? And then position 2 is immediately in front of the wind turbine, upwind, and then position 3 is immediately after the wind turbine, downwind. So position 2 and 3 are very, very close together, except is that one is in front of one is upwind and the other one is downwind. Right. Again, we are assuming a steady flow, and also we are assuming a non-rotating wake. So after the air has blown through the turbine, we are assuming that the wake, the air passing through it, is not rotating. Right? If the wake is also rotating, then some of the energy has been converted into the kinetic energy of the wake. Right? So in reality, the efficiency will be sort of even lower. But for now, let's consider a non-rotating wake. So the wake is not rotating at all. Now we can apply Bernoulli's equation to position 1 and 2. Right? We can apply Bernoulli's equation to position 1 and 2. That gives us this equation. So P1 plus rho U1 squared divided by 2 must equal to P2 plus rho U2 squared divided by 2. Right? That's the Bernoulli's equation for position 1 and position 2. Right? Position 1 and position 2. And then for position 3 and position 4, we can also apply the Bernoulli's equation. So P3 plus rho U3 squared divided by 2 equals to P4 plus rho U4 squared divided by 2. Right? So U1 is the wind speed at position 1. U2 is the wind speed at position 2. U3 is the wind speed at position 3. And then U4 is the wind speed at position 4. Right? And then P1, this small p, small case p, P1, P2, P3, P4 are the air pressure at those 4 different locations. Right? And because both position 1 and position 4 are very far from the wind turbine, it's not affected by the wind turbine. So its pressure at those 2 locations must equal to the ambient pressure. And when the ambient atmospheric pressure, we are assuming that it's about constant. Right? It's not changing too much over such a distance. Right? So we're assuming P1 equals to P4 equals to the ambient atmospheric pressure. Right? And then the wind speed at position 2 and 3 must be equal to each other. Why is that? Right? Why is that? This is actually a consequence of the continuity equation. The continuity equation basically says that the area times the speed must be a constant. Right? Position 2 and position 3, one is in front of the disk, the other one is behind the disk, but we are assuming the disk has 0 thickness. So position 2 and position 3 has exactly the same area, cross-sectional area. Right? So if the cross-sectional area is the same, then the speed must be the same. Right? Because of the continuity equation. So U2 must be equal to U3. Right? And then if we account for these 2 conditions, then we can actually subtract these 2 Bernoulli equations. So because P1 equals to P4, right? So these 2 terms cancels out. Right? And then because U2 equals to U3, right? So U2 square equals to U3 square also. So these 2 terms cancels out. Right? If we subtract these 2 equations, these 2 terms cancel out, these 2 terms cancel out. So P2 subtract P3. P2 subtract P3 on the left-hand side. And then on the right-hand side, it's rho, U1 rho divided by half, and then U1 squared subtract U4 squared. Right? So this way, we're actually getting a pressure difference in front of the turbine, upwind, and the pressure at the immediately after the turbine, downwind. Right? That's the pressure difference between position 2 and 3. we know that the pressure is basically the force divided by the area. It's basically the force per unit area, right? So if we want to get the force, if we want to get the force difference, in the front and in the back, all we have to do is to multiply the pressure difference by the cross-sectional area, which is A2. In fact, A2 actually equals to A3, right? So it doesn't really matter whether you are using A2 or A3. Here we're just using A2. So this force, this net force, is called the thrust force. Here we're using it as T. So T is the thrust force, equals to the cross-sectional area A2 multiply the pressure difference. Right? Pressure difference is here. So the thrust force equals to rho A2 U1 squared subtracted U4 squared divided by 2. Right? That's the thrust force. On the other hand, we can get the expression for the thrust force in a different way. So if we consider the entire stream tube as one object, this stream tube as one object, right? Then the force acting on this entire object must be all the force acting on this entire object must be balanced out, right? For the whole object to be actually in equilibrium, right? And we can get the force on the position 1, and then all the force and the force on the position 4, right? So on position 1, F1 equals to rho A1 U1 squared, right? This is actually from the first slide, right? Rho AV squared. But here we are just considering one component of the force, which is in the same direction as the wind. So there's no these coefficients in front of it, right? So F1 is going to equal to rho A1 U1 squared, right? And then F4 has to equal to rho A4 U4 squared, right? And then again we have to consider the continuity equation. A1 U1 must equal to A4 U4 must equal to A2 U2 because it's a steady flow, right? And then the thrust on the turbine must be equal to the difference between F4 and F1 with exactly the opposite direction in order to actually balance out the differential force on position 1 and position 4, right? So T must equal to F1 subtract F4. Right? It's not F4 must subtract F1 because you have to sort of take the opposite direction. So now it becomes F1 subtract F4. Right? F1 subtract F4 gives you what? Rho, right? A1 U1 equals to A4 U4 equals to A2 U2, right? So we can take out A1 U1, leaves out U1 here. We can take out A4 U4, leaves out 1 U4 here, right? Subtract them, that leaves us, we can replace A1 U1 and A4 U4, both of them with A2 U2, right? So A2 U2 becomes the common factor, and then U1, that's the leftover here, right? And then subtract U4, that's the leftover here, right? So that's another expression for the same thrust force on the turbine, right? And these two thrust forces must be identical to each other because it's the same thrust force, right? So this expression must equal to this expression. Rho and rho cancels out, A2 cancels out, right? And then U1 squared subtracted U4 squared can be factored into U1 plus U4 and U1 subtracted U4, right? And then U1 subtracted U4 cancels out. So that leaves out U2 equals to U1 plus U4. That comes from this factory, right? Divided by 2. So U2 actually is the average. So the wind speed at position 2 is actually the average of the wind speed at position 1 and 4. Right? Because U3 equals to U2, so U3 also is the average between the speed of the speed of the wind at position 1 and 4. The thrust force is going to create the power, right? So the power again is equal to the force times the speed here, and the force is the thrust force, and the speed is U2 here, right? That's the speed of the wind at position 2. And for the thrust force, we have an expression, right? Here we're gonna use this expression instead of this one, because this one has U2 in it, but this one doesn't, right? This one doesn't have U2 in it. So we're gonna use this expression to represent the thrust, and then multiply U2, right? Multiply U2. And the power extracted from the wind can now be expressed like that, right? Again, here we have factorized U1 squared subtract U4 squared here into U1 plus U4 multiply U1 subtract U4, right? That's the only thing that I have changed here, right? And at this point, we can introduce a quite important concept. It's called axial induction factor, and in the literature, it's usually represented as small case a, right? And this axial induction factor is actually a ratio between the wind speed reduction. That's the difference between U1 and U2, right? That's the wind speed reduction divided by the input wind speed, right? The far field wind speed, U1. So that's called the axial induction factor, right? And this axial induction factor can be used to represent both U2 and U4. So once we have defined the axial induction factor like that, we can immediately represent U2 as a function of U1 and A, right? U2 actually equals to U1 multiply 1 subtract A. U1 multiply A, right? And then U2 moves over U1 subtract U1 multiply A, right? So U1 1 minus A. That's U2, right? And then because U2 also equals to the average between U1 and U4, right? And then now you have represented U2 as U1 and A, represented U2 using U1 and A. Now we can actually bring this expression into this equation, right? And then we can actually represent U4 using U1 and A, right? So U2 actually equals to U1 times 1 subtract A, and then U4 actually equals to U1 times 1 subtract 2A, right? So that's that gives us an opportunity to actually represent the power in terms of U1 and A, right? So now we have expressions for U2 in terms of the U1 and A, and then also U4 in terms of 1 and A. And then we can bring these two expressions back into the expression for the power and replace U4 and U2 with those expressions in terms of U1 and A now, right? And then the power, with some algebraic manipulations, the power now becomes like that, right? And the power is also in terms of the U1 and A now. So U4 has disappeared, and U2 has disappeared also, right? So now it's just the U1 and A. Now what's actually the input power from the wind, right? The input power from the wind is exactly rho times A2 times U1 cubed, divided by 2. Right, that's the total amount of energy in the wind, right? Total amount of power in the wind. And then what's going to be the efficiency, right? The efficiency eta is just the P divided by P0, right? Which gives you 4A times 1A squared, 1 minus A squared, right? Again, if we want to obtain the maximum efficiency, right, all we have to do is to actually take a derivative of eta with respect to A. Set the derivative to 0 and then solve for A. Again, A has two solutions. One is 1/3, the other one is 1. Right? If A equals to 1, it means what? If A equals to 1, which means U2 actually equals to 0. Right? 1 subtract 1 is 0. 0 multiplied U1 is 0. So U2 actually equals to 0. So when the induction factor, axial induction factor is unity, U2 becomes 0. U2 becomes 0 means what? It means the speed of the wind becomes 0 when it actually arrives at the turbine. So it means the turbine basically acts as a blocker of the airflow. Right? It doesn't allow the air to pass. It's not a turbine, it's a wall. The air meets the wall, becomes a stationary. It doesn't actually move anymore. Right? It becomes a wall. It doesn't allow any air to go through it. It's blocking it. It's blocking all the air. Right? And in this kind of case, U2 equals to 0. If U2 equals to 0, the power output is 0. It doesn't matter how large the thrust force actually is, U2 is 0, right? So the power output must be 0, right? So in this case, the efficiency is 0 actually. Right? So A equals to 1, the efficiency is 0. And then what about A equals to 0, right? So suppose A equals to 0. So if A equals to 0, then 1 subtract 0 is 1. 1 multiplied with U1 equals to U1, right? So in this case, U2 actually equals to U1. U2 equals to U1 means U3 also equals to U1, right? So the turbine is not really retarding the wind at all. It's not slowing down the wind at all, right? So the wind just blows right through it without slowing down a little bit. It's not slowing down. If the wind is not slowing down, then we're extracting no energy out of the wind, right? So in this particular case, if A equals to 0, then the power output is also exactly 0, right? So A cannot be equal to 0, cannot be equal to 1, right? It cannot act as a complete blocker of the air, or it cannot act as, neither can act as a complete nor it can allow air to pass through it without any kind of retardation. It cannot, without slowing it down a little bit, right? So in principle, the turbine must act as some kind of a porous screen, right? It must allow the air through, right? But it also must slow down the air by some factor, So it must act some kind of porous medium to let the air flow through, but at the same time retard the speed by some amount. Right? So the maximum is found at solution A equals to 1/3. A equals to 1/3, right? And the maximum efficiency, eta max, actually equals to, if you bring A equals to 1/3 into the expression for eta, what you are getting is 16 divided by 27, which is about 49.3%. And that's called the Betz limit. And at this optimal A, which equals to 1/3, U2 becomes about 2/3 of U1, right? U2 is 2/3 of U1. And then U4, so it's 1 subtract 2 divided by 3, or 2/3. That's it. So U4 becomes 1/3 of U1, right? And so U4 is about 1/2 of U2, right? So if we look at the cross-sectional area, so A1 U1 must equal to A4 U4, must equal to A2 U2, right? But now we know that U4 is about 1/2 of U2, so which means A2 must be 1/2 of A4. A4 must be 2 times A2 basically, right? So A4, so that's why the tube has a very large opening in the back end, right? And then because U4 is also 1/3 of U1, right? So A4 must be 3 times bigger than A1, right? So that's why this area is about 3 times this area. Right? That's why we're actually choosing a stream tube that looks like this kind of shape. The problem with the drag-based turbines is that the blade has to move in the same direction as the wind. So the relative speed cannot exceed the free stream wind speed, which is U here. The speed ratio, which is lambda, right? The speed ratio, which is the speed of the blade divided by the speed of the free stream wind, it's always less than 1, right? Less than or equal to 1. And the drag force is actually proportional to the square of the relative speed. So if the blade moves too fast, the relative speed is going to be too low. So the force is going to be too low. If the force is too low, the power output is too low, right? If the blade actually moves too slowly, then the force is large, right? But the power, which again equals to force times the speed, can also be low, right? Because even though the force is large, but the speed is low. So multiplying them together could still give you a quite low power output. So that's the sort of the problem related to drag-based turbines. For lift-based turbines, the situation is actually quite different. It's actually very different. Again, the force is still proportional to the square of the relative speed, but the relative speed is not actually constrained by the free stream wind speed. It's not constrained by that. Because of what? Because the speed of the turbine blade is actually in the direction that's perpendicular to the wind speed. Right? It's not actually in the same direction as the wind speed. It's actually perpendicular to it. So the relative speed is obtained from the wind speed and the blade speed by using the Pythagorean theorem, right? If you consider these two speed as vectors, then that gives you a right angle triangle, right? And then the relative speed is actually the longer side of that right angle triangle, and then you have to compute. You can compute its length by using the Pythagorean theorem, right? And in this kind of case, the speed ratio, which is the ratio between the blade speed and the wing speed, it doesn't have to be constrained to be below 1. It can be actually much larger than 1. In practice, it can reach larger than 10, actually, right? So the relative speed can be much bigger than the free stream wind speed U, right? And because FL is actually proportional to the relative speed squared, so small changes in relative wind speed can bring big changes in the lift force. The constant factor CL and CD is not really that different. In practice, it's not really that different, but UREL, the relative speed, can be hugely different, right? If the relative speed differs by like a factor of 10, then the force differs by like a factor of 100. Right? CD and CL can differ by like a few factors, 1 or 2 or something, right? But FL can be like 100 times bigger than FD, and that's why those lift-based turbines are usually much more efficient than drag-based turbines, and that's why the majority of modern utility-scale wind turbines are all based on drag. Are all based on lift. Sorry about that. Are all based on the lift force.